My name is John Parker. I'm a master's student in computer engineering, so I work on hardware. But I'm also interested in system science and new technologies, and that brings me to the topic. It's a weird topic, even still. It's called artificial life. All right, yeah. And so my professors don't like it when they like artificial life, but they don't like it when anyone talks about artificial life. And there are a lot of questions related to artificial life, like what's actually necessary for life? Could it be other places? That's one of the questions in artificial life. And another big question is, we seem to be a collection of little things that do simple things, but then you put them all together and then you get us, and we think that we do some pretty complex and amazing things. And so I've come to speak about artificial life versus artificial intelligence, and distributed decision making. And to put it in a sentence, artificial intelligence kind of started as a field because people wanted to look for top-down physics kind of explanations for intelligent behavior. They wanted a simple formula that you could apply step by step, one after another, from a central location, and you could make something that resembled the intelligent behavior that you're interested in, that people exhibit, make some decisions, and explain how that happens really simply. But as you know, then, if you have ever been tasked with getting a bunch of servers in order to put something together to try and, make one of these decisions that hopefully is going to be a really good decision, it doesn't always work out just like you would expect. And so that brings in the other perspective, which is the artificial life perspective. And so rather than looking at systems top-down, we say, well, what about the bottom-up approach? That's where you have those simple things. And, individually, their behavior is simple, their decisions are simple. But sometimes when you take them all together, then they kind of give rise to more interesting behaviors, to more interesting decisions. And a nice thing about this is that it's kind of inherently distributed. So whereas you have those memory bottlenecks and data bottlenecks, in these bottom-up systems, then it's simple things passing simple information, and the idea is that you would be able to scale them, and you don't have so much of this bottleneck problem, but you do have the problem of learning kind of how to inform them to make the decisions that you want to be made. And so I have a small example here. These are Cellular Automata. Will you raise your hand if you've seen Cellular Automata? And so many people have. So this produces kind of a lifelike shell pattern. This is Rule 30 that Wolfram will talk about. And so it produces something that looks like lifelike. That's one reason why it's interesting. And then in terms of programming, I want to call attention to the fact that there are 8 simple combinations that give rise to this behavior. And so because there are 8 combinations, 2 to the 8 means that there are kind of 256 possible rules. That's 2 to the 8. And so this is for a kind of simple system where each unit only makes decisions based on its neighbor and its other neighbor. If we go to 2 to the 5, then all of a sudden there are 2 to the 32. So there are billions of different rules that are possible. So how to make this do something useful is an interesting question. And if you like to think about these things, then you're welcome to reach me at lifeuniversecomputing@gmail.com. Thank you very much.